Hello everybody, my name is Aman Bhargava, and today I will be presenting our paper, A Novel Approach to EEG Neurofeedback via Reinforcement Learning, on behalf of MannLab Canada. Before we begin, I'd like to say thank you to IEEE Sensors 2020 for this opportunity to share our research, as well as to NSERC Canada for their funding assistance on this project. So to begin with a summary, the problem that we're trying to solve here is how can EEG data be used more effectively to improve the quality of a user's meditation? Our proposal is a deep reinforcement learning biosensor feedback system where the reinforcement learning agent modulates a musical experience in real time based on the user's EEG with the goal of guiding the user to a more meditative brain state. Now, to provide a bit more detail on the proposed system, the human user listens to audio while viewing a visualization of that audio while attempting to meditate. Their EEG is simultaneously measured, and the audio is modulated by a low-frequency oscillator envelope function on the gain. The frequency of that low-frequency oscillation is controlled by the deep reinforcement learning agent. The reward function for this agent is the user's meditative state as inferred via EEG, the state space, or the other information provided to the algorithm as it makes its decision, included the rest of the EEG band powers. Finally, the actions that the agent could take included incrementing or decrementing the oscillation frequency once per second. Now, to provide a bit of background on the status quo system, neurofeedback is when the user's EEG data is directly observed by the user. Past studies have shown that this can have a positive effect on mental state, and it's even been commercialized by Interaxon in their Muse meditation app. To test our system, we created a conventional neurofeedback system by essentially removing the reinforcement learning component of the above proposed system. The user's meditative state, as inferred by EEG, was used as the low-frequency oscillator frequency parameter to directly show the user their meditation state. To test the system, we were only able to use 5 participants due to COVID constraints. Each participant spent 10 minutes meditating with each system, and the modulation parameter, EEG band powers, and meditation scores were recorded for the duration of each trial. To measure the effectiveness of each system, a linear fit was applied to the meditation score over time data. Here are some sample plots. There's a clear trend upward in this example from the proposed system. Meanwhile, we observe a more neutral trend in the conventional system. To form our conclusions, we applied a Z-score analysis on the dataset composed of the slopes of the meditation score over time from each trial. We found p equals 0.06 for the null hypothesis that there was either negative or no difference between the two systems, indicating that the proposed system functioned better than the conventional neurofeedback system for promoting a meditative brain state. In conclusion, this investigation functions as a proof of concept for reinforcement learning in biosensor feedback systems, especially in the context of wearable technology and brain state optimization. This type of cognitive response modeling could help to understand the brain's behavior, and some areas of further inquiry include longer-term testing, experimenting with alternative reward functions, for instance, attempting to promote focus, awareness, or other known correlates of EEG data, and finally, seizure recognition and mitigation. Thank you for watching this brief poster presentation. I look forward to any questions you may have about it. I'd like to thank my research collaborators, Kyle O'Shaughnessy and Steve Mann, as well as, once again, IEEE Sensors for the opportunity to share this research.